Okay, welcome back. We're gonna now dwell into the mechanisms of how one can form an enol out of a carbonyl compound. And we're gonna go through two different ways. We're gonna look at the acid catalyzed version and the base catalyzed version. So under acidic conditions, um, which would take no more than just a tiny bit of, HCl, and sometimes it doesn't need to be a strong acid. You could even use like phosphoric acid, acetic acid, to kind of enable the process to move forward. But we'll go with hydronium for this example. So the first thing that will happen is that you will protonate the carbonyl oxygen, namely the oxygen would attack the proton, and then the electrons will be dumped back into the oxygen of the hydronium. In the process, you now have a protonated carbonyl, but you also produce an equivalent of water. It is at this point that the carbonyl has been activated, and just like we saw in the previous lecture, the carbonyl is activated for nucleophilic addition, but it is also activated for an elimination to happening right at the alpha carbon. So for this mechanism, we're going to look at that. We have the water that we generated in the previous step attacking that proton. The electrons move over back towards the carbonyl carbon, and then the carbon oxygen double bond is broken, yielding the enol derivative and reforming the hydronium acid that we started the process with. All right, and just to emphasize this again, the name enol derives from the fact that you have an alcohol attached to an alkene. So alkene plus alcohol, enol. All right, and then the base catalyzed reaction, it's also rather simplistic. The first thing that happens is that you carry the deprotonation right away. So we have hydroxide in this case attacking the alpha proton. The electrons move over to the carbonyl carbon, and then the carbon oxygen double bond is broken, having the electrons relocate to the oxygen. And so you form what we call the enolate. This is the conjugate base of an enol. So the next thing is that the water that we form in that first step simply provides the source of the proton that allows for the enolate to be converted ultimately into the enol. And as you can see, you are reforming your hydroxide catalyst in the process. Okay, so the process is relatively straightforward. Now, one thing I want to highlight, however, is that especially for ketones, aldehydes, esters, the pK of this alpha hydrogen is rather high compared to water. And what that means is that if you are using hydroxide as your basic source, well, then this is going to be an equilibrium at best. And I'm highlighting that here by using the equilibrium arrow and showing you that, yeah, you're only going to be producing a small amount of the enolate because you're not really dealing with a strong enough base to drive this to completion. We'll we'll talk about which kind of bases to use to ensure that this goes to completion, but this will be an equilibrium at best. So as far as the groups that can be enolizable, most textbooks just kind of leave it at the ketone and aldehyde stage, um, and probably do mention esters as well, but they kind of leave it at that. But the reality is that all the different carbonyls that we have talked about in this class up until this point have that potential tendency. And generally speaking, the carbonyls that basically have a 3 plus carbon associated with them, like acyl chlorides, carboxylic acid derivatives, etc., all of these compounds have the ability to turn into an enol via tautomerization, but they have different strengths and different propensities to do so. So the acid chlorides, which were the most reactive molecules from the point of view of nucleophilic addition, are also the most reactive towards turning themselves into enols. And after that, you may recall that aldehydes being pretty small due to just having a hydrogen right next to the carbonyl carbon, tend to be also pretty reactive as well. So after the acyl chlorides, aldehydes tend to be relatively, okay at undergoing this tautomerization and forming the enol. That's followed by the ketones, which do have an extra carbon content, on the other side, making this a little bit more sterically in camber. After ketones, you'll notice that the thing we hit now is esters. Like esters are a little less inclined to form the enol, and you could even make the argument that this is following the pKa order of these groups, right? The lower the pKa, the higher the tendency to form the enol, and that's just because you have a lower activation energy to surmount in the process. From esters, you have carboxylic acids that, believe it or not, you can make an enol derivative from. The best way to do it is to try to do this under acidic conditions, because what that will do is protonate the carbonyl oxygen up here, and it will at that point render this CH bond rather acidic. Um, it can be done under basic conditions if you use a very strong base, but the only problem with that is that you will have to first deprotonate the carboxylic acid OH bond, and then after that you'll be able to deprotonate the alpha hydrogen, and so you'll end up with a dianion, which is not a super happy species. It can be done, but it's not recommended. And believe it or not, that's not the worst case scenario. The worst case scenario is actually amides, and the reason for that is because, unlike oxygen, nitrogen is less electronegative, and it has a more basic um, you know behavior associated with it. Namely, the nitrogen is more willing to donate its lone pair of electrons towards the carbonyl carbon, rendering this carbonyl bond less of a double bond, more like a single bond, and in doing so it diminishes the amount of dipole moment withdrawing electron density away from the CH bond. Another thing that also needs to be considered when it comes down to the formation of the enolate is that if you kind of compare it to its direct carbon-carbon analog, the allyl anion specifically, notice that the resonance structure of an allyl anion has a carbon ion here on the bottom portion of the molecule, and its resonance structure renders it on the top portion of it. But aside from that, these two resonance structures are equivalent to each other. So much so that if you think about the molecular orbital diagram, right, we have three carbons, so we're going to have three different p orbitals. So we have three molecular orbitals. We have the um, molecular orbital where everything is in phase, the next molecular orbital where you have one node going right through the middle of the molecule, meaning through the middle carbon in the molecule, and then we have the last molecular orbital where all the p orbitals are out of phase with each other. Now, considering that this is the anion, we're dealing in total with 4 pi electrons, right? Because that lone pair of electrons counts. And if you fit in the electrons in your molecular orbital diagram, you'll find out that the second orbital here is the highest occupied molecular orbital. Now, because all the central elements are carbon, there is no difference on the left side or the right side of this molecule. Basically, you have the same likelihood of attacking either carbon 1 or carbon 3, um, you know, because of the fact that they are pretty much the same element. So the electron density is the same. Now you might say, okay, well, whatever, we've seen this before with aromatics, so we're not really seeing anything new. But the point I'm trying to highlight right here is that these guys are the same simply because you're talking about the same element. But the moment that you perturb that situation and you replace carbon with something more electronegative, such as oxygen, well, now you have an interesting situation because when you consider the resonance structure, well, in one instance, you have the lone pair and the negative charge on carbon. But on the second option, you have the lone pair and the negative charge on oxygen. And out of those two options, you'd rather have the negative charge on oxygen because it's more electronegative and it attracts electrons much more easily towards itself. So what ends up happening is that for the molecular orbitals, you get something similar to what we have here for the allyl anion, except that the lowest molecular orbital um, is completely favoring electron density wise, and you can see that depicted by having a much bigger p orbital, comparison wise within the molecular orbital to the rest on the oxygen. And what this is basically telling you is that the most stable electrons are the ones that are around that oxygen. And then when you start getting into higher energy orbitals, you start seeing a reversal of that situation where now carbon starts becoming a little bit more prominent. And in the most anti-bonding orbital, you see that also, the carbon is the most prominent orbital, And another way to say that is that if you put most of the electron density on carbon as opposed to oxygen, well, you're going to make the molecule more unhappy. That's kind of the idea right here. Now, oxygen versus carbon doesn't change the fact that you're still talking about a 4 pi system of electrons. So you will still fill up the first two molecular orbitals of this enolate anion. And what I would say is that this box right here, just like the one before, is the highest occupied molecular orbital. But the difference now is that there is a vast preference for the electrons being allocated on carbon as opposed to oxygen. So you may have wondered in the past, well, if you have the enolate, and you have this resonance structure, why doesn't oxygen get to attack as opposed to carbon? Well, this is one of the reasons why. The orbital where the highest electron density is located within the HOMO orbital is on carbon. But the caveat, of course, is that the energies of these carbons have to be roughly the same to the substrate that you'll be attacking. If the energy difference between the HOMO of this molecule and the LUMO of whatever it may be attacking is very, very different, then oxygen might actually get involved. But, you know, generally speaking, since this is organic chemistry, we usually just concentrate on carbon substrates. So we'll see that the attack is going to happen through the carbanion ultimately. All right, so yes, so the HOMO minus one is benefiting oxygen a lot, whereas the actual HOMO orbital benefits carbon the most. All right, so that's how we're going to see the reactivity in all of these molecules as we go through the explanations, right? So in the next video, we're going to now look formally at how these reactions start happening. I'm going to start with simple halogenations, see how you can actually get a halogen to be substituted into that alpha position. So I'll catch you in the next video.